we'll start non-parametric regression. I want to make a couple announcements. So we'll do linear regression, non-parametric regression. Then we're going to do linear classification, then non-parametric classification. And then probably we'll do minimax theory at that point. We're going to refer to minimax results, but then we'll finally do some minimax theory. And we'll see how you get these minimax results in non-parametric cases, which is quite different from what we did for parametric cases. A week from Thursday, I'm going to have a guest lecture. So Ryan Tibshirani, my colleague, is going to come in and cover something. We'll see what it's going to be, but it's going to be something probably not on the syllabus, just to do something different. Ryan's not co-teaching this year, but he might come in and do a few guest lectures. Okay, so not this Thursday, but next Thursday he'll do a guest lecture. All right, so we're going to continue with the lasso and a few other things about linear regression before we go to non-parametric regression. Any questions before I continue? Let me remind you the problem we're solving. We're doing our prediction problem regression. The model we're trying to use, or the predictor we're trying to use, is linear. We know that when the dimension d of x is large, this changed colors on me all of a sudden. I don't know why. When this is large, we can't use least squares. So we were using the lasso, although as I pointed out, you could also use ridge regression and forward stepwise regression. So we're doing a constrained minimization, minimizing this subject to a sparsity constraint. Ideally, we wanted to minimize this subject to an L0 constraint, that the number of non-zero betas could be at most some fixed number. But we saw that that's not easy to do. It's NP hard. So we relaxed it to the L1 norm, which, as we saw, is some measure of sparsity being less than some constant. Let me make sure I use the same. I'll call it L. And one of the last points we mentioned is that the resulting beta hat has some theoretical properties. I mentioned sparsistency, that the non-zero elements of beta hat with probability 10 to 1 match the non-zero elements of the true beta, but that was only under very strong conditions. First of all, that there is a true beta, that the model is linear, and a bunch of other conditions. And also we talked about the L2 consistency. Now we want to talk about risk consistency, which we'll prove, and I mentioned it right at the end of last class. So what do I mean by risk consistency? First, we have to say consistent has to be compared to something. So since we're not assuming a linear model, we can't compare it to a true beta in any sense, but we can compare it to the best sparse linear regression or predictor, where sparse again means let me remind you what this is. We're trying to minimize the prediction error using some sort of sparse predictor, but subject to some sort of sparsity constraint. In practice, this sparsity constraint has to be chosen. We'll usually use cross-validation, we'll talk about cross-validation later. But for now, it's just some fixed number. And the true beta that minimizes this we'll call beta star. So just like in least squares, there was the best linear predictor and there was the least squares predictor. So there's a sample version and a population version. It's the same here. There's the thing that comes out of the lasso when you fit it in R or MATLAB. You get out a beta hat. It's minimizing this problem. I'm going to have to make an announcement about coming to class on time. Okay? It's very disruptive, so please try to get to class on time, all right? Because I might even start locking the door.
You have written a hard and quality constraint. What's the relationship between the hard constraint and the penalized constraint?
Yeah, that's a good question. So there are two ways that the lasso, or many problems are written. One is this, and the other one is, so minimize beta, minimize this over beta. The other one is minimize this subject to they're not quite the same problem, but they are, in a sense, the same problem in the following sense. When we actually do this, we do this for every value of lambda. I'll draw you a picture of what you get out at the end. You get a different estimator for every lambda. So you get out a whole suite of estimators. And similarly here, we're going to minimize this, but we're going to do it. I should probably put a 1 over n here, by the way, so that it doesn't matter, but that way we're talking about averages, and it matches what I wrote over here. I can do this for every possible L, and I get out a whole sequence of estimators. Those solution paths, as they're called, are identical. Okay, so you can always reframe the question whichever way is convenient.
There's always some value of lambda.
Right, there's a value of lambda such that you get the same solution for L and vice versa. And sometimes it's more convenient to say it one way or the other way.
Why do we choose to compare only to sparse linear and not the best linear in general?
Oh, well, that's a good question. I could ask, what is the best linear predictor? But that's not going to be well defined for d bigger than n. So we need some sort of constrained estimator. Now, again, ideally, we'd like to use beta 0, but now we're in that world of where it's NP hard. We can't do it. So we're settling here on L1 norm being some measure of sparsity. Okay?
Why not compare to the true estimator use 0 norm?
I'm sorry?
Why not compare to the one use 0 norm?
So why not take the population version to be the 0? We'd like to do that too, but they won't be the same. And in fact, in general, you don't approximate that estimator.
But as the true estimator, but I think the 0 norm is the one that we want.
That's the one we want, but it's not going to give us that. We don't have a way of getting that. I agree. The ideal would be the 0 norm. Yeah.
There is a way, I think there is a way to prove that these two minimization problems are equivalent by using the envelope theorem. Because
Using the
envelope theorem, because there is a kind of like it is a Lagrange of the other.
You're talking about these two?
Yeah.
No, he was talking about something else.
Oh, okay.
He was talking about why not put a 0 norm here. Yeah.
So there are no results.
Oh, there are results that show you when they're equal, but the results are under this following incredibly strong assumptions that they're the same. Those assumptions will never hold in practice, so they're not very useful results. Actually, let me retract that. They're not useful results for what I think of as typical machine learning and statistics problems. There are certain domains, like in signal processing, where those assumptions make sense.
I just want to know, why do you want to compare this big pi to this star? Because since the thing that we want is that the estimate we get is near to the solution to the 0 norm.
Maybe. I mean, that's just a matter of definition.
We cannot get any intuitions about that.
No, that's not true. This is another notion of sparsity, right? I spent some time convincing you in the last class that the L1 norm does measure sparsity in some sense. So there is a sense in which the solution to this problem is the best sparse linear predictor in a certain sense. I agree there's other senses, like beta 0 instead of beta 1, but that's just a matter of definition. So L1 norm does measure sparsity in some sense. So this is a type of best linear sparse predictor. Okay. But we don't even know yet that beta hat and beta star, or rather the risk based on beta hat and the risk based on beta star are the same. So now we're going to prove that. This is theorem 13 on page 12. And let me also define r hat of beta. Which is just the training error. Now, for simplicity in this proof, I'm going to make everything bounded. It's not required, but then the proof and actually even the statement of the theorem gets more complicated. So I'm going to assume all the y's, the x's are bounded by some constant b. Okay? And then the statement of the theorem is with probability at least 1 minus delta, the prediction risk of the lasso estimator, how well we're going to predict with the lasso estimator, is less than the prediction risk of the best sparse linear predictor in that sense, plus some, I'll put the constants here, although I'm not sure how important the constants are. What's more important, I want you to notice, is the rates. So we know it's not going to be as good as this. There's going to be a bit of slack. But how big is the slack? And these are constants, right? So you see it's going down like root n. Where does the dimension come in? And the interesting thing is it only comes in logarithmically. That's important. So that's why this is in some sense an explanation. I'm not saying it's the only explanation, but it's an explanation of why the lasso works for high dimensions. It's because you're approximating the risk of the best linear sparse predictor up to some term where the dimension only enters logarithmically. And let's prove this. We can use some simple concentration of measure to prove this. Any questions about the statement of the result?
So the only difference between these two estimators is this one is from population and the other is from...
Yeah, this is what we compute from the data. This is sort of what we'd like to have. That's the population quantity.
B for the x.
Oh, I didn't. B is, I said all the random variables are bounded by some constant b. So it's just a constant. All right, so here's the proof. First of all, we have a new pair, x, y. Let's just start calling that z. And similarly, we'll call each training pair zi for convenience. And here's another convenient piece of notation is I'm going to define gamma, which is actually a function of beta, to be minus 1 beta. I'm just going to add a minus 1 in front of beta. And the reason for doing this is if you look at this predictive risk, well, really, this is the first component, or the last component of z. This is the rest of z. This is beta, and now there's a gamma here, a 1. So this is really just gamma transpose z squared. It just makes it's going to make all of the notation far more easier, but also it makes it clear we're just dealing with some sort of quadratic form. This is nothing other than, gamma transpose gamma, gamma transpose lambda gamma, where lambda is the expected value of z transpose. Right? Because this is just, you can just see this is just gamma transpose z here, and then we're squaring it and taking the expected value. So what that makes it clear is the risk really and this is for any arbitrary fixed beta. And remember, this is really gamma of beta. Okay, so this is the parameter here. This is something about the population, the covariance essentially the covariance between the features and y and the features and so on. So that just makes it sort of clear what the predictive risk actually is. And if we do the same thing for the training error, it's exactly the same argument. The training error is nothing other. This is again for a fixed beta, where this is just the sample version of this. Okay. So that's helpful, but I really want to compare, this minus this. So I'm just going to subtract now these two quantities. So if we now look at, let me try the other piece of chalk here. This chalk, for some reason, has some sort of special effect where it keeps switching between, I don't know if you can tell that, it's switching between yellow and white kind of randomly. So I'm just subtracting those two things. Sorry, that's not what I meant to do. Correction. Before I compare beta to beta hat, I want to do a preliminary step, which is compare R and R hat at a fixed beta. So just pick an arbitrary beta for the moment and compare R hat to R. Well, the only difference is the middle of that sandwich there. And so what we get is that's gamma transpose lambda hat minus lambda. Okay. And what is that? Let's just actually write out what this is. This is, a quadratic form, so it's a double sum. So this is actually the sum, the double sum, j and k, and it's gamma j, gamma k, and then it's lambda hat. I'll just write the jth, kth element this way. I'm just writing out what the sum is, right? But I'm going to bring the absolute value on the inside. So that's less than or equal to the sum over j and k of gamma of j, gamma of k, lambda hat jk, lambda jk. Did I define what that is yet? Good. There's a little typo here, but delta n. Yeah, okay. Look at this double sum. Let's give a name to the maximum of that over j and k. So let delta n equal to max j which we'll figure out what that is in a minute. So this is less than or equal to its maximum, so I'm going to pull that out. That's less than or equal to delta n. What is left on the inside? What's left? It's sort of like the norm. It's a double sum. Yeah, but which norm is it? L1. This is just the sum of the absolute values. So the sum breaks, this is really two sums, right? J and K. And I can break it into the sum over J, sum over K, and it's the L1 norm. See how naturally the L1 norm arises? And you get it twice. So what I've got is the L1 norm of this squared. So the L1 norm kind of popped up naturally here. And if you look at the way I define gamma, what's the L1 norm of gamma? It's 1 plus the L1 norm of beta, right? So this is less than or equal to gamma n. And remember, we're doing this restricted minimization subject to the L1 norm of beta. There it is, less than L. So this is less than L plus 1 squared. So we haven't bounded this yet. We'll come back to that. That's where our concentration of measure comes in. But what we've discovered is just by the nature of the lasso and how it's formulated, the empirical risk and the true risk are bounded by this L1 norm squared and this random quantity delta n. Okay? And so we're going to bound delta n in a minute. But before we do that, let's now let's now get the a bound on the quantity we're interested in. I'm sorry? Yeah, there's a lowercase delta in the notes. I don't know where that came from. Well, I do know. I must have forgot to type capital D. So yes, that appears to be a typo. Jisoo, you're supposed to be checking those for those typos. He's close to perfect. Where is Jisoo? Not here. Oh, that's why he didn't show up. He's close to perfect. Much better than I am at finding typos, that's for sure. Okay. Before we bound delta n, though, let's bound the risk now. So we're going to use a string of inequalities that we've used before for bounding risk, which is the following. Very, very simple but useful thing. We're interested in this. Yes. We just figured out how far apart r and r hat are. So I can say this is less than r hat of beta hat plus that stuff. Now we use the fact that beta hat was chosen to minimize this. So if I put any other beta in here, it can only get bigger. So I'm going to put in beta star. Now we do it again. I know I can replace r and r hat. I can switch them around. I know I'm introducing an error of that size, so that's less than r of beta star plus another term of that size, 2l plus 1 delta n. So we're almost done. The risk of the lasso estimator is less than the risk of this ideal estimator plus this error. The only thing, yes?
Should you have a square?
Probably. Was it square?
L plus 1 squared delta n.
Thank you. The last thing I need to do is bound this. How big is that? Then we're done. What is that quantity? Let's just think about what this is. You know, lambda is some big matrix. Lambda 1, 1, lambda 1, 2, lambda 2, 1, da, 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 da. But these are all just moments, right? Those are expected values, everything in there, of some component of z with another component of z. Lambda hat is exactly the same thing. It's just the sample moments. So each one of these is a moment. Each one of these is a sample moment. Everything's bounded. We can use our old friend, Hoofting. So the difference between this and this, that is the probability, that's what delta is. Let's call it delta jk, is bigger than epsilon using Hoofting's inequality directly, gives us 2 e to the minus n epsilon squared. The range of these variables, it can get as high as plus b or minus b. So hopefully I've counted things right. I got 8b squared. You're good at that. The guy here in the green, check that. It might be 16, might be 4. What's your name? What's your name?
Jen.
Jen. Okay, he'll check. Jen will check whether I'm off by 2 or something like that. Now the maximum, I'm just going to do the union bound. So the maximum of this is less than or equal to, how many guys are in the matrix? Well, most, let's say, d plus 1 squared. So I notice there is already a mistake because I wrote d squared. But actually, don't forget I enlarged z to include not just the x's but the y's. So there's a small error here. There should probably be a d plus 1 squared. But d plus 1, yeah. And in fact, if we just say there's d minus 1 covariates, then it's correct. And then we get minus n epsilon squared over 2b squared. And now all I do is I set this equal to delta, because I want this to be true, except on a set of probability delta. And I can solve now for epsilon. So we get epsilon is 4b squared over n log. Let me correct this. So this is d plus 1 squared, and this one should be probably d plus 1. And what
This is lambda is symmetric, so this scale looks enough to make bound.
Oh, yeah, I'm being a little bit loose. So first of all, there really aren't d plus 1 squared because it's symmetric, right, and so on. So yeah, it's being I'm being very conservative here. But the order of the bound is correct. And so what that says is, therefore, with this choice of epsilon, the probability that delta n is bigger than epsilon is less than delta. So with probability at least 1 minus delta, I can say this is less than that epsilon. And the important thing again, so the constants don't really matter. The important thing is that this is something like, think of this as being like log of the dimension over n. If the dimension had come in polynomially, this wouldn't have been very useful. This is what allows us to do high dimensional regression. Okay, so those are we only proved one of the 3 main results on the last. So remember, there's also the sparsistency and the L2 consistency. Those proofs are a lot longer, and as I've said, the assumptions are extremely strong. So I find this result to be more useful and more interesting, and just by coincidence happens to have a much shorter proof than the other results. Okay. We haven't talked about cross-validation yet, because in practice you're not going to just pick an arbitrary sparsity level. We're going to do that later by cross-validation.
So in general for this result, there's no assumptions, right?
There are no assumptions on this result except for IID. We're not assuming the true regression function is linear. We're not assuming that the design matrix has any nice conditions or anything like that. It's what you might call a distribution-free result. So there are similar results for forward stepwise regression, but as I mentioned, it would take too long to go through them. But they are in the notes if you're interested. Yes?
L1 norm is the only norm that we get logarithmic dependence on D? Or like,
Sorry?
so L1 is the only norm where we get logarithmic dependence on D?
Oh, no. So this is also, you can do similar results for other norms and other loss functions, but it's just it just happens that because we're doing the lasso, everything works out into the L1 norm. But you're asking, is that what causes the logarithmic dependence? I'm not sure if it would.
At least for this technique is
Certainly for this technique, yes. But I wouldn't rule out that there's other ways to get logarithmic dependence. In fact, no, the answer is no, because the forward stepwise, you'll see the results also have a similar flavor to them, yeah. Okay, so that's an introduction to some of the concepts behind high dimensional regression. Before I go on, though, is there any questions about that?
So if you didn't assume boundedness, what would you
in general, if you don't assume boundedness, you have two choices. So there's sort of several directions you can go. People often assume sub-Gaussianity, which you've dealt with before, which basically means thin tails, small changes to the proofs then. If you allow for long tails, thick tails, you often have to change the proofs quite a bit, and in some cases you have to change the techniques quite a bit as well. If you want, so in fact, that's something that's been ignored a lot in high-dimensional regression, frankly. So if you want to have some fun, try doing simulating a high-dimensional regression function and put in, you know, the Cauchy distribution, which has no moments. Try generating Cauchy errors and see what happens when you run the lasso. You're going to be kind of surprised. So when you get to really thick tails, I think actually the methods have to change. You need to do more robust methods that aren't sensitive to extreme observations. You know. So usually we do sub-Gaussian or bounded because we get a clear, intuitive picture of what's going on. But it really does matter, actually. Those are not innocuous assumptions. Any other questions? All right, I want to tell you something else about sparsity that it's one of the dark call this the dark secret of sparsity. Sparse methods are great because, as I've mentioned before, they have a real practical utility. So, you know, I'm trying to predict something based on 20,000 proteins, and keep measuring 20,000 proteins is very, very expensive. But if I can find a sparse predictor based on 10 proteins, it's going to save us a lot of money and time. But even in the ideal world, where all these nice assumptions hold, and everything's sparse, and we have the sparsistency and all that, sparse estimators can still behave poorly in some cases. And that's because sparse estimators, you know, they have a kind of almost a lack of smoothness to them. You know, things are zero or not zero. And that's, generally speaking, in statistics not a good thing. Statistics works well when you're taking averages or you're taking smooth things. Those are kind of the really summary of statistics right there. So I want to show you a result. There's these two guys from, I forget whether they're from the Netherlands or Germany. One of them's a friend of mine, so that's a bit embarrassing. But Lieb and Pocher. And they have a whole series of papers. They're very vehemently kind of against all this sparsity stuff. Unfortunately, no one listens to them. But they have interesting things to say about it. And I'm just going to do I'm going to do one of their theorems. It's a small snapshot of their results because we just want to do something that we can prove here in class, which shows that if you have a sparse predictor, and even let's even consider a really ideal case that the model is correctly specified and even low dimensional. Let's keep the dimension fixed. Sparse predictors have some unexpected properties. They shouldn't be unexpected, actually. Let's test everybody's memory. Do you guys remember in 705 I mentioned something called the Hodges phenomenon, the Hodges example? Does anybody remember that? A few of you remember it, not many of you. Because I didn't spend a lot of time. Yeah, right. I don't know what that meant, but it seemed correct. It's really just the Hodges phenomenon coming back to haunt us, okay? The Hodges phenomenon was when you're trying to estimate the mean of a normal. If x bar gets close to 0, you just set it equal to 0. So there's this jump in it. And it appears like that's going to actually help you, but then you discover that because the risk function looks really good, but then when you look very close to 0 but not quite 0, the risk function looked bad. And so this is an old thing, you know, in statistics, and people seem to have forgotten it in sparsity. So I'm talking here about theorem 14. It's just sort of a cautionary tale. There's some conditions. Let's not worry about too much about the conditions. Just imagine we're doing regression, finite dimensional. So we'll keep D fixed, assume it's correct, the model's correct, it's linear. We're in kind of an ideal world. And let's assume the errors are mean 0, finite variance, all the nice stuff. But we're going to assume that beta hat is sparsistent. In fact, we're going to even assume something weaker. We're going to assume it's weakly sparsistent. What does that mean? It means that the probability when the true value of beta, the regression says, we'll denote it by beta, that the indicator function for some component, let's say beta j hat, is 1, is less than the indicator function from the true coefficients one for all j goes to 1. So what is this saying? All I'm saying is that if one of the beta j's is 0, then this is 0. That means the corresponding beta hat's 0. So I'm correctly recovering the zeros of the vector of coefficients. So, and if that holds, as n goes to infinity, we'll say it's weakly sparsed. The only reason why it's weakly is we're not requiring both to get the 1s and 0s right. We're only requiring just to get the 0s correct. Okay? And here's the cool thing. If this holds, if you have an estimator which satisfies this condition that everybody wants to hold, apparently, then if we look at the risk over beta, and let's look at the L2 risk. Why am I multiplying it by n? Because we're in a finite dimensional situation, and we know that the mean squared error goes to 0 at a rate like 1 over n. Right? The bias squared plus the variance. For a parametric problem, fixed dimension is like 1 over n. So to keep this at a fixed scale, I'm multiplying it by n. And we're looking at this minimax risk. I'm going to show you now in a few lines that this goes to infinity. Okay? Whereas what would happen if I did the least squares solution? The least squares estimator, it turns out, for linear regression, finite dimensional, correctly specified model is actually the minimax estimator, as it turns out. And the risk goes down to 0 at a rate of 1 over n. Or if I multiply by n, it's bounded. So for least squares, in this case, you actually get that this is bounded by some constant.
What's the risk of the lasso lag under different loss functions like higher exponents?
What is the risk of the lasso under different loss functions? So you'll see actually this proof is for arbitrary loss functions, and the result is that it goes to the maximum value that the loss can take.
So no matter how many times I exponentiate that difference that's less than 1,
Yeah, I mean, the way I actually stated it was that the expected value of the, if you look at equation 15, the expected value of any non-negative loss function goes to the maximum value the loss can take. So this is a little bit surprising, and people don't talk about this, but this is saying, the risk is terrible here, whereas the least squares estimator is good. Of course, if d is bigger than n, the least squares estimator also isn't good. So we have to view this result with some caution. But it's just something to think about. Let's prove it, because most of it's pretty easy. I'm going to leave one step out that requires something that we didn't cover in this class or in 705, but it's a small point. But let's prove this. In fact, let me state the general result first, because we're going to prove the general result, that the expected value, we're going to have some function. Think of this, I stated it for squared error, but let's take it to be root n beta hat minus beta for some general L. And the claim is that this goes to the maximum possible value that this function takes over all s. So that's infinity for the quadratic. How are we doing on time? Oh, good. We're doing really well, so I can get through the whole proof pretty easily. And the proof is quite simple. So here we go. You ready? We're going to pick an arbitrary s, some vector in our D. Okay? And I'm going to look at a sequence of vectors beta that are getting closer and closer to 0. They're going to be, in fact, equal to minus s over root n. So this, again, for those of you who remember the Hodges phenomenon, it's when you get close to 0 that the risk starts to screw up. And I'm explicitly constructing such a sequence. So the point is, first of all, that let me do the proof. I want to try to get it on one board because it's very simple. So that's the setup. Let's just prove it over here. Here we go. Here's the proof. So the sup over beta of the expected value under beta and if you prefer, think of L again as just the quadratic, so just square that. The sup over all betas is certainly bigger than or equal to that particular choice of beta. So we've constructed, for each n, we've picked out a particular beta, and that's just one guy in this set. So of course, the sup is bigger than the value there. And that's bigger than or equal to, if I multiply this by something which makes it smaller, then it has to be bigger than or equal to that. So in particular, I'm going to multiply it by L root n times the indicator function for whether, I'll just do, beta hat, let's call it. So beta hat, well, here's beta hat. So I'm multiplying this by something which can only be 0 or 1. So I can only make it either the same or smaller. And this is around the whole thing. But when beta hat's 0, of course, this goes. Right? So this is equal to, what do I get? I get L of root n times minus beta. This isn't even random anymore. So that's actually L of minus root n. All these betas should really be beta n here. Well, this one at least. Right? So this is deterministic, this term, on this event. So I pulled it out front. And the expected value of an indicator is a probability. So that's the probability under beta n. But if I look at beta n and multiply it by minus root n, I get s by construction. So this is equal to L of s times the probability under this particular beta n that beta hat is equal to 0. Everybody with me? Now, by the sparsistency assumption, we know that when beta is 0, the probability that beta hat is equal to 0 is going to 1. This is the whole point. We're using this sparsistent estimator, which says that if all the betas are 0, then my beta hat's going to be 0 eventually, with probability 1. What can I say about the probability under beta n? Well, beta n is very close to 0. And using this is a very subtle thing called contiguity, that when two probability measures are very close together, the things that they say have probability 1 or 0, they agree on. So if you want to check this, assume the distribution is normal, and you can check this yourself. You'll notice in the statement of the theorem, I didn't assume normality. It's true under weaker conditions. But just check it under normality. It's pretty easy. That this statement implies that since beta n is very close to 0, that this must also be true. And again, just take beta hat to be normal and just integrate it and see what happens. You'll be able to convince yourself it's true. But it's actually true much more generally. This is something called contiguity. And a little history lesson. I mentioned Lacombe many times in 705, who invented many concepts in statistics. This is another concept due to Lacombe, is this notion of contiguity. That part we're going to just leave it out, okay? So this is tending to 1. So what we've just shown is that with probability going to 1, with probability tending to 1, the sup of that guy is bigger than or equal to eventually L of S. But S was an arbitrary point in the space. This is true for every S. So therefore, it's bigger than or equal to the sup over all S, which is what we claimed.
So in the first step, how do you switch from sup beta to e beta, beta n?
How did I get from here to here?
Yeah, yeah.
Oh, well, this is one element of this set. So the maximum of our whole set is bigger than the value at one point.
So where does the beta n appear? The beta n doesn't appear in the.
It's here, and it should. Is that, did I get, yeah, it's also, so more typos in the notes there. Those should be beta n's. Jisoo, come on. I'm going to just keep blaming Jisoo for, he'd be horrified if he, he's probably going to watch the video too. And just kidding, Jisoo. What's going on is setting things equal to 0, which is what's going, all these estimators are, is a very unstable property. And intuitively what's happening is if you have if the true coefficient is very close to 0, it's really, should you set it equal to 0 or not equal to 0? That's a very unstable decision. And that really screws up the loss. That really makes the risk high.
Does in minimax sense, the ridge estimator could be better than?
The ridge estimator will be much better because it's a smooth estimator. Now, how is it that there's all these theorems and papers about this? You'll notice in a lot of the papers about sparse recovery, they make a very odd assumption. They either assume that all the betas, they say the betas can only be 0 or big. They don't allow betas like this. And they never comment on it. But now you know why they're having to make this assumption. You're not going to get good risk. So it's kind of a weird assumption. You're either assuming the betas are 0 or they're pretty big, but they can't be anywhere in between, which is a bit odd.
But in this case, so we get the worst case when all of the betas are like very close to 0, right?
The worst case is when the betas are not 0 but close to 0.
But that means there's no regression at all. There's nothing to predict.
Actually, it's quite the opposite. This is the most interesting case statistically, right? When people are doing drug trials, the drug might have no effect, beta 0. That's an interesting case. Or the drug might have a huge effect, beta's 15. You don't need a statistician. You don't need a machine learner to solve those problems. The reason why we're spending billions of dollars looking for drugs are those small effects. That's actually the most important case. So you're kind of, yeah.
Isn't it also kind of weird that beta n is going to 0 with n?
No, not at all. That's what uniformity is all about, right? This is why we're always talking about uniform things, is you want to make sure things hold uniformly, and a sequence is just a special case of that. So if you look at any paper about hypothesis testing, the theory of hypothesis testing, they always let the alternative go to 0, as n goes to 0. And fixed beta, your aunt can solve the problem who's never taken a statistics course. Right? It's the subtle cases that we have to invent all of this theory for.
What is the expectation taken over once the beta means?
What is the expectation taken over? Well, I didn't say, but we're generating random data from some regression model and estimating the beta hat. So it's with respect to that randomness.
But what we know by E beta? The beta is is the true estimator?
No, this is the true value of the parameter. We're doing a regression problem, and this is the true parameter value. Didn't I say that? So yeah, I actually forgot to say that in the setup of the theorem, but we're doing regression here. In other words, you're assuming this, and there's some true beta. This idea of taking, these are called local alternatives.
But is that beta binary value?
No, this is a regression problem, right? This is just some vector betas.
which you take like square root n, can be considered like another rate?
No, that's special. Square root n is, the rate at which things are hard to distinguish statistically. This,
But in the definition of the weakly sparsing, we use equal to 1. Should that be not equal to 0 or something like that? Why we let this thing equals to 1?
oh, yeah, you're exactly correct. Another typo, equation 12, that should be 0, not 1. Sparsistant, or not, I guess it's either 0 or not equal to 0. Equation 12, we're checking whether the beta hats are equal to 0 or not whether they're equal to 1 or not. Yeah, thank you. Wow. This page has been in the notes for like 4 years, and nobody's ever caught that before. It's amazing. Makes me wonder how carefully people are reading the notes, right? Let me say that these local alternatives, as this is called, is a really foundational thing in statistical theory. And it should leak more into machine learning. That nobody cares about the theory for easy cases. Anything works in easy cases. Considering local alternatives is really what allows you to, it's like putting a microscope down and looking carefully at what's going on and how does this work. So for example, if you were doing a hypothesis test, and you make up 2 tests, one good test and one crazy test, at any fixed alternative, they all have power going to 1. And there's nothing to distinguish those. If you really want to see if you have a good test, compare how what the power is for an alternative that's not 0 but getting closer to 0. It's a way to zoom in and look, and then that allows you to distinguish good tests from bad tests. So this trick is something which shows up in a lot of statistical theory. And in terms of machine learning, I'm trying to think if I've even seen it, probably in a few papers, but not many papers. But it's a good thing to know about. If you want to check if something's going wrong or not, checking these local cases. But let's talk about the bigger picture here. Does that mean you shouldn't use sparse estimators? No, I'm not saying that. Okay, so don't take the wrong conclusion here. Because, for example, in a really high-dimensional regression problem, you may not have a choice. There might be nothing else that we can do. I just wanted you to be aware that you read a lot about sparsity in the last 4 or 5 years, and you get this feeling that it's, everything's roses, but there's prices to pay for sparsity too. Everything has costs and benefits, that's all. And so there's good things about sparse estimators, but they can have unpleasant properties as well. So I just wanted you to be aware of that.
You can also use ridge in high dimensions.
You can use ridge, but yes, which is much safer, but if you really want to get a small set of predictors, that doesn't help you, right? So, yeah.
Another thing, you were saying something about this particular rate, like the square root n. If it was like s over n would be like easier or something like that. You were saying that this was like...
Square root of n is special here, right? If you took n or n to the 1/4, you'd have different. This wouldn't happen.
What is weakly sparsity? The definition of weakly sparsity? That should be not equal to 0.
0. Oh, yeah. We want to make sure that when the true beta is 0, that you get beta hat 0.
Right. So it should be beta j not equal to 0.
Yeah, instead of 1, you mean?
No.
Oh, sorry.
I mean, when the true beta j is 0, the right part of it, the indicator function is 1. So in this case, the prediction, whether it's 0 or other values, it's less than or equal to 1. So the equation here should be not equal.
Oh yeah, you're right. It should say beta j not equal to 0.
Right.
Yes, I agree. That was the typo. Yes. Sorry if I wasn't clear about that. Right. Okay. Any other questions? All right. Good. There's a very, very short section, section 5, which has 1 sentence or something in it, which is inference, which is how would you do confidence intervals and so on for the beta after doing the lasso. That's a very, very, very difficult and actually controversial problem. So I only put it there to let you know that the problem exists. And if you're interested about it, that could be one of the topics we do later in the course. Right now, we're just focusing on prediction, not inference, just using the lasso to do prediction. So we can come back to that if there's interest in that. Okay. There's also something in the I put in the appendix. Two things in the appendix. One is something called L2 boosting. Those of you who know about boosting, you can use it for regression as well. And so if you're interested, it's there in the appendix. It's not critical, so I put it in the appendix. And also some of the details of the proof for the forward stepwise regression are also in the appendix because they're kind of messy. Sorry, hold on. Could you
You mentioned that this implies that you should not use sparse estimators have inferior.
I'm not saying you shouldn't use sparse estimators. I'm just warning you that they have some unpleasant properties. So don't go and say, Larry Wasserman told us we should never use lasso. I'm not saying that. I use it.
Is it possible to do like ridge regression that can at least tell us if we are in this sort of case, and if we aren't, then we can safely do L1 to get a sparse estimate?
No. So that's a good question. Could we do some sort of screening method to tell us whether it's safe to do this or not? But see, you're just putting the problem back one step. You're going to still end up with the same problem. At the end of the day, you either have a sparse distance estimator or you don't, and you're going to have this problem. You're just sort of getting, what's that, like turtles on top of turtles on top of turtles, you know. All right. So we're going to move on to non-parametric regression. Let me just summarize, though. You know, low-dimensional regression, easy. We did least squares. In practice, there's a lot more to low-dimensional regression because least squares, for example, is very sensitive to outliers and influential points. And there's a whole art to doing low-dimensional regression. That's why we have a whole course in it about how to check the model assumptions, how to see if the regression is fitting properly, how to do robust things so that you're not affected by outliers. So I don't want to oversimplify linear regression either. You know, I made it look very simple in the notes, but in practice, it's non-trivial. But at least at a theoretical level, it's simple. Least squares, the properties are well understood. High-dimensional, ridge, lasso, forward stepwise, probably the three most common things. There are now, as many of you might know, many, many, many variations of those things. The group lasso and various other extensions of all of these things, right? Fascinating area and obviously very useful. Okay, I'm going to move on then to non-parametric regression unless there's any other questions about linear regression. So non-parametric regression. As the name implies, we're departing from the linear regime. The terminology here is interesting because you could say what we just did was non-parametric because even though I was using a linear predictor, I never assumed the true function was linear, but still we were using linear predictors. But now I'm going to allow myself more arbitrary predictors. So we're going to call that non-parametric regression. So again, we're assuming that the regression function is fairly arbitrary. There's two reasons for using something non-parametric. There's non-linear, non-parametric. One would be just it's a wider class of predictors, so we might get better predictions. So from a purely predictive point of view, we might want to consider things beyond the linear regime, right? But then there's other situations too where maybe you want to estimate that true m, which now becomes possible, or at least more possible in some sense, if we use non-parametric estimators, because we don't have to assume linearity. So if you have the notes, I hope you do, and you look, for example, here's a nice data set. This is a low-dimensional data set. And this is just a one variable thing. What this is showing is bone mineral density. You know, your bones have a certain density to them. And it changes with age. And what this is showing you, these are scatter plots of change in bone mineral density for females and males as a function of age. And maybe I don't know if you know this or not, but what happens is, as you get older, your bones get denser up to some point. So it looks like what, about 13 is peak bone mineral density for women, and about 15 maybe for men. And then it comes down as you get older, as you probably know, right? And if you're interested in that function itself, so this is a non-parametric regression estimator. And it's pretty clear that to get insight here, fitting a linear regression is not going to be very helpful. Both from the scientific point of view, trying to understand scientifically the relationship between bone mineral density and age, and from the predictive point of view. I'm obviously going to do better predictions if I fit something which is not linear. Okay, so that's a very simple example. It's only one-dimensional. We're going to eventually consider high-dimensional things. Here's example number 2 is only 4-dimensional. Things already start to get complicated, though. This example is, the Y is a measure of disease progression for people with diabetes. And X1 to X4 are various things that are being measured. Age, body mass index, and some blood serum measures. And we'll see that one approach would be to do a fully non-parametric thing jointly in all 4 variables. But one of the other things we're going to talk about is how to break it down into one-dimensional non-parametric regression functions. So something called an additive model, which is a sum of smooth functions. We'll talk about this. This is not as non-parametric as this. This is saying we're going to let this be an arbitrary function of x1 to x4. Linear regression would say let it be a sum of linear functions. Something in between that we'll talk about is let it be a sum of arbitrary functions. It's in between the 2 extremes. One of the advantages of this, well, the disadvantages is not as flexible as this, obviously, right? It's not as non-parametric. On the other hand, you can get a nice plot like on page 3, which allows you one at a time to show how diabetes progression, how it relates to age, body mass index, and these blood serum measurements. You can visualize it quite simply. One of the problems in high-dimensional classification and regression is visualization. Sometimes who cares in some cases, right? If you just want a spam predictor, you don't want to visualize the classifier, presumably. But if there's a scientific question you're trying to answer like this, visualization is kind of important. We have to be able to look at the function. And it's not obvious how to look at an arbitrary 4-dimensional function, let alone a 400-dimensional function. So we'll consider all of these things. We're going to look at a whole class of different types of estimators, which all have different benefits and advantages. We're going to consider mostly kernel estimators, something called local polynomial estimators, which don't get used as much as machine learning, but I want to convert you all into local polynomial estimators. And we'll talk about reproducing kernel Hilbert space estimators. And I'll deprogram you on that. So I think they're overused. And then a couple of other things. And then Ryan might give a guest lecture on a completely different way of doing it. The thing about non-parametric regression is we could have a whole course on it, like many of the topics here, because there are so many different types of non-parametric regression. So we're really going to focus on what I think are the most commonly used things. And the kind of questions we're going to consider. Yes?
Could you clarify again the distinction? Because in many places for linear regression, people say that it's linear only in the parameters and we allow functions of the data points.
Yeah, we'll come to that point. That's the notion of linearity, you're right, is maybe a little bit slippery because a lot of these non-parametric estimators are going to turn out to be linear smoothers, for example. But that doesn't mean that they're linear functions. And some of them are linear functions in a different space. But right now, I'm just think this. This is linear. This is not. I just mean in a simple, basic looking at the function sense. But there are subtleties. So in section 2, there's a little reminder just of bias variance breakdown. I'm not going to go through that. That's just to remind you. We've talked about that before. Right? Any estimator, M hat, there's going to be some bias and there's going to be some variance. You already know that. And there's also going to be a notion of minimaxity. In these notes, I'm going to state some minimax results, but we're not going to prove them till later in the course. And they're going to take the following form. We're going to say if I take the sup of the regression function over some large class of possible regression functions, and I take the minimum over all estimators, and I look at some risk function, we're going to want to know. So this maybe I should call Rm. We're going to want to know, is my estimator minimax over some class? Okay, and so for this set of lectures, I'll be stating them, but not proving them till later. And the minimax rates, I'm going to tell you, always take the following form. I'll try to write that more clearly. You've seen things like this before, where beta is some measure of smoothness. Roughly speaking, how many derivatives we're assuming about m. And d is the dimension. So we're going to see things like that popping up. We've seen them before. Okay? So let's start. How are we doing on time? Good. Let's start with the simplest, and the oldest, the simplest, and in some cases the best estimator, I think, in some senses. I should say almost the best, because we're going to use what's called a kernel estimator, and then we're going to improve it, because it's got some deficiencies. Now, this is not kernel in the sense of Mercer kernel and reproducing kernel Hilbert spaces. Okay, this is a different use of the word kernel. I wish we'd invented a different word. Maybe local averaging estimator would be a better thing, but anyway. It's very similar to the kernel density estimator that we talked about in 705, but it turns out to have some differences. So what's the idea? We're going to have this thing called a kernel. This is going to be any non-negative, smooth, symmetric function, and our canonical example is the Gaussian. So just think of the Gaussian, and I'll draw this in one dimension. So this is going to apply in any dimension in principle, but say we have the bone mineral density data. We're going to look at the data, and now I have to produce an estimator m hat, but I have to do it at every value of x. I have to produce a function. The estimator is a function. So for any value of x, what I'm really going to do is just take a local average of the y's. In fact, one way of doing a kernel estimator is just to take a window, a slice, and just average those y's, and then slide that across. A slightly more refined way of doing it is to put this kernel down, and now just take the average of the y's, but use these as weights. So that means we're going to do something that looks like this. Let me use the same notation. Yeah. I'm at a particular x, but I'm averaging over all the data. There's going to be a bandwidth. Remember, the bandwidth is the width of this. Think of the standard deviation of the normal. However, that's not quite enough. We have to divide through, and this is where it differs from kernel density estimation. And the reason why we have to do that is the following. If I take this thing, let me call this, did I give it a name in the notes? Yeah. I'm going to call this whole thing, it's a weight, the ith weight, and it depends on where we're doing this, say Li of x. So I can write this as yi times the weight Li. The weight depends, though, on each data point. If you're over here, this data point has a high weight, this data point has a low weight. So this weight is a function of the target point that we're estimating at. The reason for dividing through by this is to make sure the weights sum to 1. The reason why we want the weights to sum to 1 is it seems like one property you'd like to have is that if I just gave you constant data and I do the smoothing, I should just get back the constant. And you can check you need the weights to sum to 1 for that. But in general, if you want a weighted average means you have a bunch of weights that sum to 1. So if we want to think of this as a weighted average, it has to sum to 1. So that's why this is on the bottom. Okay? It's just to normalize these weights. As we saw in 705, for kernel estimation, the choice of kernel is not very important, either theoretically or practically. Any smooth, symmetric function will give you almost identical results. What really matters is this bandwidth h, because as h goes to 0 or infinity, you're going to get very bad predictions, if you're thinking about it from the prediction point of view, or very bad function estimator if you're thinking about it from the point of view of estimating the function. And the reason why, well, what happens, so what's going to happen when h goes to 0? What kind of estimator do I get out? You're just going to interpolate the points. It's not even well defined in between the points, but basically it's going to just interpolate the data. You're overfitting. This is h small. You're overfitting. You're going to have very bad prediction error because the variance is going to be large. Variance is large. If I let h get really big, actually, what do I get as h goes to infinity? What is my regression estimator as I spread that kernel out? Constant, which constant? Y, the mean, y bar. So we have very high bias. So your predictions are not going to be very good, or your function estimator is not going to be very good. So we're trying to strike a balance here, as usual, between the bias and the variance. Okay, so I've drawn this in one dimension, but this could be d-dimensional. That's why I put the norm there.
In the multivariate case, the kernel has to be rotationally symmetric?
It doesn't have to be, but usually it's rotationally symmetric. So this would typically just be a multivariate normal, or the way I wrote it, it's a univariate normal, and I put the norm in, which makes it rotationally symmetric. There's actually work on using anisotropic kernels, it's called, but I think it's pretty rare people would actually do that in practice. Okay, so in the last few minutes, let me just state this theorem on page 5, and which I think is very, very important. And as you're going to see, it illustrates a problem with kernel regression, but it's easily fixed. Okay, so one of the advantages of, so we have to need, so to distinguish this type of kernel regression and reproducing kernel Hilbert space regression, which we haven't got to yet, maybe I'll call it smoothing kernels and Mercer kernels. Okay, this problem affects other types of regression too, but it's easily fixed with smoothing kernels. I'm not sure how to fix it with Mercer kernels. Okay, so let me tell you what the problem is first. So I'm going to tell you what the mean squared error is. This is theorem 5. I'm doing this equation 15. This is for, I wrote it down first for the one-dimensional case, just because it's much easier. This is a pretty messy theorem. The conditions are messy. The expression is messy. And we're going to do a proof outline. I'm not going to do the full proof because it's actually very long, although it's not technically complicated, but it's just long. But let me state the result first and say what the problem is. So let's look at, what I'm doing is I'm fixing an x. This is not random. So the randomness is over the training data that goes in the m hat. And I'm just asking what's the MSE. And the MSE is the bandwidth, h to the 4th over 4, times the following complicated looking term, m double prime to m prime of x, p prime of x, p of x, times this constant, just call it mu2. I know this is a long expression, but bear with me. Okay, let me explain what's going on here. So this is the bias. actually the bias, yeah, that's the bias. This is the, this is the bias squared. This is the variance. This is the remainder term, which can be shown to be of smaller order than these terms. So that's why we're ignoring it. And here's the problem with kernel regression, but I think the same thing happens to reproducing kernel Hilbert space regression and many other regressions, but we will fix it next week or on Thursday. It's this. And he's saying, why is he pointing to that thing? What this shows you is that the bias depends on the derivative of the, what's p? P is the density of the x's. It's kind of odd that that should come into it. This is called design bias. What this is saying is anywhere where the density of p is a little bit steep, has extra bias. That's called design bias. And this shows up, this in practice, this is nasty. Because if there's weird, a lot of times you have regressions where the data don't fall nice and smooth. They fall kind of like on manifoldy kind of things. This is huge. Okay? There's a second problem which isn't contained in this theorem, which is if you're anywhere near a boundary of the support of the distribution, the bias is huge. It's much bigger. It's not of order h to the fourth. It's much larger. So many, many types of non-parametric regression suffer from these two things. Design bias, which means how the x's are distributed is somehow having a profound effect on the bias, and boundary bias. And by the way, in high dimensions, you get more and more data near the boundaries. That's one of those counterintuitive things about high dimensions. That there's a lot of data near the boundaries. So this becomes worse in high dimensions. Okay? And we're going to prove this on Thursday, or at least outline proof where this comes from. The cool thing is the fix is trivial. People actually spent years coming up with complicated methods to remove the design bias and the boundary bias. It turns out there's a very simple fix, finally people realize, called local linear regression or local polynomial regression. Very easy to do, very easy to program. Gets rid of the design bias, gets rid of the boundary bias. And the reason why I'm emphasizing this so much is this is an example of something I don't think is penetrated from the statistics literature into the machine learning literature so much that I'm aware of. And it's kind of an important point. So what will happen then is, let me outline on Thursday the proof. Then I'm going to talk about the multivariate version of this. Then we'll talk about these local polynomial or local linear in particular smoothers. And then we'll move into some other versions like penalized smoothing and reproducing kernel Hilbert spaces.
So, we have this issue with bias. Are we going to be able to do that independently of the variance? We're actually going to be able to
Yes, the cool thing, that's a good question. When I get rid of this bias, am I going to increase the variance? No. So that shows you it's unnecessary bias. Yeah. Any other questions?
The expectation is it's only over the data to construct the estimate.
That's the only thing random here is the training data. Because this is at a fixed x.
And what is the norm of k?
The norm of k is just the usual L2 norm of the function. Any other questions? Good. So then we'll continue this on Thursday.